I want to say a little bit more about one of the problems that I had started but not really finished discussing in class. And that's this idea of a roller coaster, where we ask what is the normal force required at the top of a loop for a mass E equals 200 kilograms, V equals 10 meters per second, radius equals 5-meter roller coaster. And just for approximation, I'm going to take G equals to 10 meters per second squared. Now, what you have to remember about this is that at the top of the roller coaster, the right way that I think to think about this is to say at the top of the roller coaster, there are two forces acting on the car. There's the weight, mg, and there's a normal force. And if I pick a coordinate system so that it's pointing inwards here, may as well call that plus x. Doesn't really matter what I call it, but I know that I have to have an acceleration in that direction going towards the center of magnitude v squared on r. So I know that the acceleration in this case has to be v squared divided by r. V and r are given in the problem. And I know that the sum of the forces in that direction is going to be the two forces here. They're both pointed in that direction. mg plus n has to be equal, provided the acceleration, and that sum of the forces has to be providing this acceleration. Therefore, the acceleration provided by those forces is the sum of the forces over the mass, and that's equal to mg plus the normal force divided by m. Now you'll notice I'm being very careful not to write MA over here because that would introduce this notion of centrifugal force, which I'm kind of trying to avoid to keep things intellectually clean here. Okay, well now I just equate the acceleration required with the accelerations provided. So I know that v squared over r is equal to, I'm going to divide through here, g plus normal force over the mass. And then I can solve for what n is. Oops. And so I will subtract g and then multiply by m. So I'm going to get that that's equal to v squared over r minus g all times m is equal to the normal force. At this point, I am just plugging in values. So let's go. Normal force is equal to 200 kilograms times the speed squared, which is 10 meters per second squared, divided by the radius, which is 5 meters, minus 10 meters per second squared, and that is equal to 200 kilograms times 10 squared is 100, divided by 5 is 20, so it's 20 meters per second squared minus 10 meters per second squared, which is 10 meters per second squared times 200 kilograms is 2,000 newtons. Now I want to ask, what if r equals 20 meters? Question mark. So in that case, I get the exact same formula. Nice thing about working things algebraically. And I just plug in different values. Well, then I get that my normal force, N, is equal to 200 kilograms times 10 meters per second squared, or 10 meters per second quantity squared, divided by 20 meters minus 10 meters per second squared. For that case, we have that that's 200 kilograms. Again, it's 100, but instead I'm going to divide by 20 here, and that leaves me with 5 meters per second squared minus 10 meters per second squared. Oops. Don't close that bracket. minus 10 meters per second squared. And in that case, that's equal to negative 1,000 newtons. This negative sign tells me something's gone wrong. That tells me that the normal force is pointing opposite the direction that I've drawn it in my coordinate system and I set up. But there's a problem. The normal forces in a roller coaster can't act upward. It's pushing on the center of the circle in this roller coaster path, and therefore it can't push upward. Maybe something like glue could exert that force. But what this means is that the negative, since this is less than 0, that means normal force required would be upward. And if that can't happen, we get roller coaster falls off track. And that means lawsuits. All right, all done, and good luck.